Okay guys, so we're going to be talking about trigonometric identities for a few days, several days. Some people say this is the hardest part of any pre-calculus class. Alright? You can think of trigonometric identities as geometry proofs. Remember when you did geometry proofs? You guys had to make a table, and you had statements on one side and reasons on the other side. You guys remember doing that? Yeah, most people do hate that. The hardest part about that is all the critical thinking and having to justify everything. But another part of that whole thing that people hate is just the amount of writing. You know, people don't like to write. Well, I have good news for you and bad news for you. The good news is you don't have to write any reasons for these proofs. Okay? So if you happen to use what's called a Pythagorean identity while you're working, you do not have to tell me that you used it. I can tell from your work that you used it. Okay? The bad news is these problems are fairly challenging. Okay? Quite difficult. So let's first talk about what an identity is, and then from there we'll talk about some of the theorems that you will use in your proofs. Okay? They're not called theorems now, they're called identities. But they're like the theorems. Okay, so first thing you need to know is that two functions are identically equal if they are equal for all x values in the domain of f of x and g of x. And an equation of this sort is called an identity. I will explain this on the next two slides. But for now, you can just write it. Okay, so I'll read it one more time. Two functions are identically equal if they're equal for every value that is in the domain of f of x and g of x. An equation of this sort is called an identity. Okay, so what we're talking about before I move the slide is, imagine you had something written like this. This would be called an identity, okay? It means that f of x and g of x are really the same function, even if they don't look like they are. Okay, for example, I might write x equals cube root of x cubed. Is this statement sometimes true, always true, or never true? Always. The statement is always true because the right side is just a messified version of the left side. Messified is my own word. It's the opposite of simplified. You could say that the left side was just a simplified version of the right side is all, or the right side is a messified version of the left side. Let's take a look at one other word here. Some equations are true conditionally, okay? But some equations are true always. An identity is true always. I'll put always in quotations. You'll see why in a minute. This is just an easy way to understand the idea. Some equations are true conditionally, but an identity is true always. For example, this first equation right here, this is true if x is 1. This is true if x is 1. It is not true always, right? On the other hand, this is true always. What do I mean by always? It means it doesn't matter what x is. If x is 0, it's true. If x is 1, it's true. If x is 1,000, it's true. Let's go back to this left column. This is true in two cases. I'm going to give you a second to see if you can figure out what two numbers make this true. You can just write them down. Don't shout them out, please. There are actually two numbers that make it true. Second period, I had a student guess both answers. Third period, I had a person solve the problem and get two answers. One of them is definitely 5. Most people can just guess that. 25 minus 5 is minus 20 is 0. Did you get the other answer?
Yeah.
What do you think it is? Negative 4. Yeah, so guys, we don't need to solve these sorts of things in our head, right? That's why we learned algebra. You factor this, right? X minus 5, x plus 4. Algebra was invented so you wouldn't have to guess answers anymore. That's what algebra is for. It's so you could think less and do more, and you still get the right answer. It's a tool. Okay, what about this last, statement on the right, actually? Let's go to the statements on the right. This one is x plus 1 equals x plus 1. That thing's true, just like x equals x. Look at this one here, though. This almost looks like the same problem as this one, x squared minus x minus 20 equals 0, but it says x squared minus x minus 20 equals x squared minus x minus 20. Does x have to be 5 in this context? No. X does not have to be 5. X does not have to be negative 4. This is just true in general. X could be 0, x could be 1. You get negative, 20 equals negative 20. So it wouldn't matter. No matter what happens, basically all this stuff just cancels out. You get negative 20 equals negative 20. When is that true? Always true. So you'll see in a minute why I'm saying always in quotations. Okay? Question?
Yeah. If two equations set equal to each other yield undefined, are the undefined equal to each other?
That's a good question. That's where I was going to go next. Okay, actually, I was going to do one more example, and then I was going to talk about the undefined case. All right? This statement is true for certain angles on the unit circle. Okay? There are some angles in the unit circle that make this true. Most angles make it false. For example, tan of 30 degrees and sine of 30 degrees are not the same. But tan of 0 and sine of 0 are the same, aren't they? Tan of 0 is 0. Sine of 0 is 0. So if theta happens to be 0 degrees, this statement's true. And it also happens when you get to 180. Sine of 180 and tan of 180 are both 0, see? So this thing is true under certain cases, under certain circumstances. Whereas this one over here is true always. So there is an interesting situation on this last one, and that just came up actually. And that is, what do you do in the case of pi over 2, for example? Because pi over 2 is an exception to what I'm saying, because technically tan of pi over 2 and sine of pi over 2 and cosine of pi over 2 in ratio aren't technically equal because neither of these exist. This is 1 over 0, right? And this is 1 over 0. Is 1 over 0 equal to 1 over 0? No, they aren't numbers.
Then what are...
Is infinity equal to infinity? No, they aren't numbers. It's important to understand what's a number, what is not a number. You can't say things like infinity equals infinity. Nor can anyone say my infinity is bigger than your infinity. That doesn't make sense either. Those aren't numbers. They aren't numbers. You can't talk like that. It's bad jargon. So this statement here, you might say, well, hold on, Mr. Shore, this isn't true always. This is true only when you're doing numbers make sense. You're right. But that's what I mean by always. When I was stating that these are always congruent, or always equal, I had this in quotation marks, which is my way of explaining that this is true for every value that is in the domain of f and g. Pi over 2 is not in the domain, so I don't even have to consider that case in this problem. So this is still an identity at the bottom, even though it doesn't work when you plug in pi over 2. Okay, question. Is this an identity? 1 over x equals 1 over x. Is it an identity?
Yes.
It is. Now, we know that it has a problem when x is 0, but that's not in the domain anyway. You're not supposed to be looking at that. For all numbers in the domain, for all the non-zero numbers, this is perfectly true. How about this one? 1 minus x, 1 minus x. Is this an identity? Yes. Of course, we have to be careful what x's we pick, but for all the x's that we do pick that are legit, they're equal. So this is still an identity, despite domain issues. You guys think this is an identity? Do you think this is sometimes true or always true? Or never true?
Sometimes.
Getting a little hard to tell. This one's only sometimes true. Watch close. If I change this to a plus, it's always true. But how can you tell? These are the kinds of problems we'll be working on for the next 3 or 4 days. You'll be given a problem that looks like this. You will be asked to show that this is always true. All the problems you do will be always true, and you just have to show it. So somehow you have to convince me that this on the left is the same thing as this on the right. But there are rules. You have to simplify the messy side until it looks like the simple side. And you cannot cross multiply, and you cannot move anything across the equation. In fact, once you pick the messier side, you're not even allowed to touch the simple side. You just leave it there, and you mess around with that until it says tan theta. And that can be very hard to do. But that's what we're going to do.
And you convert cotangent theta to 1 over tan theta.
Yes, one of the ways to do this problem is to change this to 1 over tan theta and to work with it as a complex fraction. And if you do that, you will find that you really are dealing with tan theta. It's just a very messy version of tan theta is all this is. Okay? The messier one side is, the more steps it takes to get it down to what it looks like on the other side. So it's just like doing proofs in geometry. This question would be written like this: verify, which basically means prove. It's the same word as prove. It means show that this is true. Can you convince me that this is really tan theta? And like a proof in geometry, you have to use all the theorems that I give you over the next 4 days to accomplish this stuff. But unlike geometry, you do not have to write down the name of the theorem that you are using. So it's a proof without the reasons column. You can think of it that way. So that's good news. Bad news, it's proofs. Good news, you don't have to state your reasons. I can tell from your work what your reasons are. Okay, so the rules for simplifying the left side are called identities, not theorems. And let's get started on the first couple. Okay, so here's one. We know that tan theta is y over x is a definition. Right? This is not something I made up. Someone made it up years and years ago, and no one's ever changed. You know, you can't change it. It's just there in the math dictionaries. It's not something you have to prove. It's just something someone made up. Okay? So I don't need to prove that. That's just I just grabbed it from the math dictionary. We also know that sine theta equals y over r and cosine theta equals x over r are also definitions. They're both just definitions. I don't need to prove that to you. You can just look it up. So I cannot change them. Those are just facts. But I can combine them or manipulate them. So what I'm going to do is I'm going to take these definitions, which are just facts, like nobody can contest them, and I'm going to use them in my proofs. So what I'm going to do is I'm going to take sine theta equals y over r, and I'm going to multiply both sides by r. And I'm going to write it this way instead. Y equals r sine theta. Y equals r sine theta. Okay? You will use that 1,000 times this year. And probably 500 times in calculus. What I just wrote in green. Super important. It's in chapter 6, it's in chapter 8, it's in chapter 9. It just goes on and on and on. Okay? Super important. Okay? How about this one? Cosine theta is x over r. What happens if I multiply both sides by r? I get x equals r cosine theta. equally important. But if I take these two and I insert them into the definition at the top of the page, right? Tan theta is y over x. I can now write that as r sine theta over r cos theta. And what happens when I manipulate and substitute facts into one another or into an equation, you create new facts. So what I have here is a brand new rule of my own making, you could say, that tan theta is sine over cosine. And you should be able to reproduce this proof. If I ask you on a test to prove that tan theta equals sine theta over cosine theta, you should be able to go through something similar to what I just did using x and y and r. This thing has a name, many of them do. This is called quotient identity number 1. Quotient identity number 1. I will leave it to you to supply an equally simple proof to show that cotan theta is cosine theta over sine theta. So you show that cotan theta is cosine theta over sine theta. Okay? This is quotient identity number 2. I'm stating it without proof, but I think you can fill in the proof yourself over here or something tonight. I'm not giving you homework tonight. Just go back and fill in the identities I didn't prove. You can prove them yourself. Okay? Okay, so you'll prove that second one. Let's go on to a new concept. Let's take another formula that we've seen earlier in the year. How about this statement? We saw that cosecant theta is r over y. This is a definition. Can't we insert now an r sine theta here? We showed on the previous page that y is r sine theta. It's even green still. We just created a new identity. What is it? Cosecant theta equals what?
1 over sine.
1 over sine theta. So you might say, no, that's not new. I knew that. That's not an identity, Mr. Short. It's just a definition. It's not a definition. The definition is that cosecant is r over y. It just so happens that that means 1 over sine. Okay, question?
Yeah, for the cotangent theta that you want us to prove.
Just follow my steps. It's just a little upside down.
No, I was just wondering if we could just like substitute that for 1 over tan.
No.
Oh.
We don't have that theorem. Do you have a theorem in your notes yet that says cotan theta is 1 over tan theta yet?
No, you have a theorem. Well, you can do the math to show that cosine over sine is equal to 1 over tan.
Yes, that's what I'm hoping you'll do.
Oh.
Yeah, you need to follow a similar argument to what I did. You can't use facts like tangent or cotangent theta is 1 over tangent theta. I haven't stated that yet. That'd be like using a theorem from chapter 3 in your geometry book when you're back in chapter 2. You can't do that. Okay, so if you're going to prove this one tonight, okay, this one down here, your work should look exactly like mine, okay, except things are upside down. Don't try to bring in other facts, because I don't have any other facts. These are my building blocks. I'm building as I go. Okay? This thing has a name too, guys. This is called reciprocal identity number 1. Pretty simple, and you've even seen it before. I will leave it to you to show that secant theta is 1 over cosine theta. That's basically reciprocal identity number 2. And what do you suppose the third one is? Cotan theta is 1 over what? tan theta. That one's a little bit harder than the secant one. But this is reciprocal identity number 3. See if you can figure out those two tonight. And that is based on what I did right here at the top of the board. I did it with cosecant. You can try it with secant and cotangent. Now you may use cotangent is 1 over tangent from now on, because it has been stated and proven. First you prove it tonight, then use it as much as you want after that. It's mathematics, folks. You don't use a theorem until it's proven. It's not a theorem until it's proven. It's a postulate. Okay? Question?
Will we have proofs on the test?
Yes. Lots of them. Yeah. You know what they really are? They're just a bunch of substitutions and rewritings until things work out for you. Ultimately, remember, our goal is going to be to show things like this are true. So you'll be simplifying this thing. It could take you 5 minutes to get it to look like this, but it will work. And then your last statement will be this, and then that'll be the end of the work. And I have to grade everything. I have to see all the steps that lead between this and this, and all the way down I have to see that this never changed. This has to be simplified to that. Okay? Every time you do a substitution or a change, you have to be thinking about one of these identities or one of these identities. These are your theorems. These are your bank of facts that allow you to make substitutions. Okay? All right. The last ones are the Pythagoreans. So what have we been doing? We've been writing down old XY statements and substituting in r cosine theta and r sine theta for x and y respectively. So there was a rule earlier in the year that was written like this. Does that look familiar?
Yes.
What would happen if we put r cosine theta in for x and r sine theta in for y? What would happen? Let's see. We're going to create a new rule. By the way, this is just Pythagorean theorem. I'm not even going to argue with that. There's 250 proofs for it, at least. Everyone knows it, so I'm not going to prove it myself. But we'll start with that fact, and we'll substitute in r cosine theta and r sine theta to see if we can generate a new fact. Okay, squaring the r and the cosine, you're basically doing r times r and cosine theta times cosine theta. It looks like this. R squared cosine squared theta. That's how we write it. It means cosine of theta squared as a quantity. And then this would be r times r and sine theta times sine theta, which we abbreviate like this. And it's funny that we put the square on the end there, but that's what we do. That's just how we show it. And then the r squared cancels out. Question?
Yeah. Is that what we would type the sine squared into our calculator?
Different calculators have different rules. If you have a TI-89 and you want to type sine of 5 squared, you can type it like I just wrote it, or you can type it like this on a TI-89. The safest thing to do is to type it the first way, because I think the TI-84 requires that.
Is it probably better just to find the answer first? That's what it's
This is called the Pythagorean identity number 1. There are 2 more. I'd like you to look at the book and see if you can figure out what they are. We'll go over them tomorrow.
Is this sufficient proof?
So what we're going to do with this is we're going to take this existing identity and we're going to actually manipulate it to create 2 new ones. Okay? I'll do the first one and then you do the second one. So like this. What would happen if I took cosine squared theta plus sine squared theta equals 1 and simply divided everything by cosine squared theta? You might say, why in the world would you do that? You'll see in a minute why I'm doing it. For now, it just looks like I'm playing around. Let's try and simplify that. This is definitely just 1. What is sine over cosine? Didn't we already say what that was? What is sine divided by cosine? not cotangent. It's tangent. And so this is like sine over cos is what it is. That's what it means. Sine times sine, cos times cos. So you actually have two tangents there going on. So this is just tangent squared is what that is.
1 plus tan squared equals cosine.
Yes, and 1 over cosine, we know that 1 over cosine is also known as secant, right? So this is actually secant squared. So not only do sine and cosine share this nifty little Pythagorean relationship, but so do tangent and secant. Interesting. Who would have ever thought that tangent and secant share any relationship whatsoever, you know? They're totally different ideas. But this is Pythagorean identity number 2. It came from the first one, which means if you forget the second one, you can always rederive it very simply just by dividing. Divide by the first term and you get this brand new relationship. That's for the student who doesn't like memorizing a lot. And then, what would have happened if we had divided by sine squared? So, I'd like you now to try that. So don't shout out the answer. That's never appropriate. I want everyone to try it. We're going to divide instead by sine squared. Maybe we can get a relationship that's different still. Like a third Pythagorean. Try that now. All right, so what does our first ratio come out to? This is cotangent squared. Yes, and then this, of course, is 1. What is 1 over sine? Cosecant. So what is 1 over cosine, or what is 1 over sine squared? Cosecant squared. So this is yet a third identity, and that's kind of where it ends. We don't need to do any more. What we've seen is now sine and cosine share this neat little relationship at the top of the board, and tangent and secant share a relationship, and cotangent and cosecant share the relationship. So in the past, we've never seen these related to each other in this way. Also, this means that when we're working in mathematics, if we run into something like tan squared, okay, instead of being intimidated by that, we realize immediately that there's a replacement for it. You can replace it with secant squared minus 1. Or let's say you're doing a really complicated problem, you see a secant squared just chilling there on the paper. That's really 1 plus tan squared. You might need to make that substitution, or it might make your life more convenient, or whatever. Okay? All right, now, these are powerful in proofs. They are like theorems to use for proofs. Okay? But they can also be used for other things. So let me show you real quickly how some people use these to their advantage, especially when they don't have a calculator. This is kind of cool, watch. Let's say that I asked you, let's say I told you actually, suppose sine theta was 2/5, and I asked you to find cosine theta. You can use this first rule up here as it's almost like a formula. You can just plug 2/5 in for sine theta right here. So watch this. It'll be like this. Cosine squared theta, which I don't know yet, plus 4/25 equals 1. I just plugged in 2/5 where it says sine squared. And then that means that cosine squared, if you subtract the 4/25 over, is 25/25. Or sorry, 21/25. And then I can square root both sides, and I learned there's actually 2 answers to this question. So I used the Pythagorean identity as sort of a formula to jump from knowing sine to knowing cosine, see? And I can do the same thing with the tan and the secant, or even the cotan and the cosecant. And now what's cool is I could ask you, okay, what is tangent? And you actually don't even need this formula. You can just say, well, I've got sine and cosine. I'll just divide them to get tangent. See? Or if I ask you what is cotangent, just do this divided by that. See? Pretty neat. So with all these neat relationships, the more you know, the easier trig becomes.